Yeah, so we finished Wednesday's class talking about this problem. Just to remind everyone what was going on here is that we had a simple system. This is just had a transfer function for the plant of 1 over s times the quantity s plus 1, and we wanted to then take some sort of control design measures for the center point, right? And so there's I believe the formula of the rise time and the overshoot of the system. And so we went through a few things, right? First we went through and said, all right, can we just do the simplest thing possible, use proportional controller, and understand whether or not that the proportional controller will ever get us there in terms of meeting these specifications. And this is what this plot on the left here shows, is that the root locus gives all the possible closed-loop pole locations as we vary the single gain. This is our proportional gain, and we see that this never intersects the region of interest in the complex plane. And so our analysis here would be that a proportional controller will never reach the design specifications given to you. Right? So we have to do something a little more complicated. And so the strategy that we're using here is use a lead controller, which is a standard type of controller. It has the form of this lead controller in the upper left here. And what this is effectively doing is bending the root locus plot. So this red line here, red line, this is the previous root locus. And this is what we want. Right, so we said that if we add a pole and a 0, and the 0 is farther to the left than the pole is farthest to the left than the 0, what it's going to do is it's going to shift this asymptote to the left so we can pull the root locus to the left and then allow us to place closed-loop poles in the desired location. So that was the strategy here. And so we were able to, via the angle law for the root locus, well, one, we had a rule of thumb for the 0, and then via the angle law for the root locus, we could then calculate what the pole location should be to make sure that the root locus goes through some sort of point of interest, and this is -4 plus 6i because that was in our design region. Okay. And so then what we did on during Wednesday's class is we calculated where this pole should be, and the result is that the pole should be at 34 radians per second. Right here. All right. And so now we have determined two of the three factors, or parameters of a lead controller: the 0 location, the pole location, and yet to be solved for is the K, or the gain on the entire system. All right. So that's where we're going to start off today's lecture, is calculating this gain. Before we do that, though, I want to just plot the root locus plot for this system, just so we have kind of a remapping of it, and just to see another example with root locus plots for your notes. So going through this, we're going to plot this in figure 14.9. We're going through the rules. One is that the number of poles in the open loop system is going to be the number of branches. So we had, in our plant, we had 2 poles. And by adding a pole to the lead, with the lead controller, we now have 3 poles, right? We've added a pole or dynamics to the system by adding this lead controller. So this is going to be 3 open loop poles. Therefore, we're going to have 3 branches of the root locus. All right, rule two, we have 1 0. So keep in mind the plant had no zeros at all. But the fact that we added a 0 in the lead controller means now that our combined dynamics has a 0 in it. So we have m is equal to 1, n is equal to 3. So then we have n minus m is equal to 2. Branches go to infinity. Okay, so note that this is exactly the same as what we had for the plant, because when we added the lead controller, we added a pole and a 0, right? 1 of each. So therefore, we haven't changed the difference between these. So that means, since we haven't changed the difference between these, this is rule 3. That means asymptotes are going to be at negative 90, positive 90, exactly the same calculation we gave for the case of proportional control. And then here's one of the aspects of which this will be different. All right, so we're going to look at the asymptote intersection point. We are summing up so we're summing up all the zero locations. Summing up all the pole locations, dividing by m by n. So for this particular example, we have a 0 at negative 6 from the lead controller. And then we have poles at 0 and negative 1 from our plant itself. And then we've added a pole at negative 34. And this will all be divided by 1 minus 3. All right, because we have this number. Okay, throw this in a calculator or calculate by hand, and we get negative 14.5. Okay, so just as a point of comparison here, if we look at our previous root locus plot, we had an asymptote intersection point of negative 1/2, right? And now we're at negative 14.5. So we've actually pulled the root locus asymptote to the left considerably by adding a pole and 0 in the locations that we did, right? So we're moving everything to the left too. Okay, so then plotting these items here, so we have, for plot this on the root locus plot, we have pole at the origin, pole at negative 1, right, 0, a 0 at negative 6, and then I have a pole that's way off my chart. It's somewhere over here. Negative 34 doesn't show up on my page here. It's over way to the left here. Okay, but it's still in the system, right? It's just way off my chart. Okay, construction lines. Okay, so I have an asymptote at negative, what did I just say, 14.5? All right, that's barely off my chart. I can still somewhat approximate this. This is going up plus or minus 90. And then I can add more elements of this. So we have that the root locus on the real axis is to the left of an odd number of poles and zeros. So over here, to the left of 0 poles and zeros, and here, to the left of 1 pole and 1 0, or sorry, just 1 pole. All right, go over this pole, I'm to the left of 2 poles. And I go over this 0, I'm to the left of 1 pole and 1 0, 2 poles, which is 3. So that means that the root locus lies in between here as well. Okay, and then completing this is essentially matching our sketch that we basically saying, all right, what do we want ideally? So we said that we design such that the root locus directly goes to the point negative 4, 6i, and negative 4, negative 6i. Right, so that's a kind of a waypoint. Once you do some of these design tools, you can actually say, we force the root locus to go to this point. So this is not an approximation. It will directly go through the point negative 4 plus 6i. So this can help you draw the root locus plot as well, because this is kind of a waypoint in between. And so what we're seeing here is that we know that a 0 is going to attract one of the branches of the root locus, and we know that the root locus is on the real axis between these points. So this one's obvious, right, what's going on. We know that these branches, you can't have the branch connecting a pole and a pole, so this must break away from the real axis and catch up to this asymptote. And we also know now it must go through this point. Right? So this starts to complete the picture for us. Yeah.
So could you also use this to have a perfect zero cancellation? Like if you force it to randomly through a point, could you perfectly cancel the zero if you wanted to?
Yes. Yeah. And then the most common way in which you'll see this is, all right, so say for instance, is like, I'll erase this in a second, but say for instance, as a thought experiment, I had a pole, say here, in my plant, and I don't want to worry about the dynamics. Since the kind of the rule of thumb is to place a zero around the natural frequency, and if I want to simplify the system, I would just place it right on top of it, and it would make things a lot easier for me. Okay, so then completing this root locus plot, what we see is it has to break away from the real axis. It's going to break away at plus or minus 90 degrees. The exact point it breaks away, I'll calculate in a second, but I figured it better to show like the general idea of what's going to happen first. But this is going to be our new root locus plot. All right, so we've, I talked about there was a lot of questions about design, and we were just talking about root locus plots itself before we got into that design. I said, okay, we're going to morph the root locus plot to be more desirable. This is exactly what I'm talking about. All right, so we've significantly changed the shape of the root locus plot by adding poles and zeros. Yes?
Can you detect where exactly the singularity point is, or do you just like approximate that?
Yep, I'm going to do that 1 second. Yeah. The breakaway point. All right, so any question about this general concept here? Okay, so this singularity point, which is in the notes defined as rule 7, but I've kind of run myself out of room here, so we'll do it over here. No, I don't like that because it's going to be out of order when you're not looking at two planes. So let's do edit. All right, now it'll be in order. Yep, so 7, so the breakaway points. Okay, so we have, remember the formula for this, we look at what's the numerator. So the numerator here is n of s is equal to s plus 6. This is what we designed it to be. The denominator is going to be equal to s plus 1. These are the poles coming from the plant, but we also added a pole from our controller, s plus 34. And so if I were to multiply this out, this would be s squared, or sorry, s to the third, plus 35s, s squared, plus 34s would be d of s. So I'm going to be using the function that's derivative of d of s with respect to s, n of s, minus derivative of n of s with respect to s, d of s has to be equal to 0. So looking at derivative of d of s with respect to s, that's going to be 3s squared plus 70s plus 34. N of s is s plus 1, or s plus 6. And then we have derivative of, minus the derivative of n of s with respect to s, right? So this is then just 1 with this derivative. S cubed plus 35s squared plus 34s all equal to 0. Okay. So this, I'm not going to multiply this out. This has to be solved with a calculator. It's a third order polynomial. You would not be able to do this by hand in any reasonable amount of time. So by calculator, we would find that the values of s such that this equality is true are negative 13.527i and negative 0.52. Okay, so 3 roots. Yes? Yeah, thank you. Okay, so 3 roots, but there can only be one answer. So which one's correct here? So which one is that? Okay, thank you. Yeah, so 0.52 is the one that makes sense. So remember, going back to the root locus plot, so we'll circle that. That is the one that makes sense. Going back to the root locus plot. All right, so it has to break away from the real axis, and it breaks away from the real axis. It has to break away on a point on the root locus. The other 2 options are not in the real axis, right? Those are complex numbers. This is the only one on the real axis, and it's also in a region where the root locus exists on the real axis. Carson.
We were trying to get the root. Why don't we have to do the quotient rule so we've got the n of s possible?
Yeah, so you are going back in the notes to slide 13, which is, or lecture 13, right, which is where this originally comes from. So you're exactly right that you would have n of s, I believe, squared on the bottom, right? Right, but we're setting this all equal to 0, so we can get rid of that term, right? We just multiply both sides by n of s squared.
Well, isn't there a chance, though, that n of s is equal to 0, so that it'd be a non-real answer, or it'd be an infinite answer?
Yeah, so if n of s is equal to 0, then it's going to be infinite, which is not going to be equal to 0. All right, so the original, if you use the quotient rule, just so everyone's on the same page here, this would be all over n of s squared, but we can always simplify this because the right-hand side is equal to 0. Okay. All right, so this is the breakaway point. I drew it just quickly because there were not a lot of options in terms of, this cannot move too much to the left and too much to the right. It was kind of confined in between these 2 poles here, so I just went ahead and drew it. But that would be the actual breakaway point for this. Okay, so this is what our new root locus plot looks like, and we said that we want to make sure, so the first thing we did is we want to say, okay, I want my closed loop poles to be at negative 4 plus 6i and negative 4 minus 6i, yes?
When would this be useful to calculate the sigma?
The asymptote location. That's more for, so I would say in terms of design, the most useful aspect is actually placing a pole directly where you want it, which was the angle rule that we used just prior to this. This is what we used on Wednesday. So calculating sigma A here to figure out where the asymptote is more to complete this root locus plot in terms of teaching all of you to understand what happened to the root locus plot. Okay, so once you do the design, where the asymptote is not all that important because you care about where the dominant poles are placed, not where the asymptote is if we crank up the gain to infinity. Right? It's just to show everyone what it looks like. Yeah. Yes?
So like this sort of part of this process we couldn't really do on the exam, right? Because it's like you never get like a solvable. You couldn't get a second order. Like you can't find the right point necessarily by hand.
If it's second order, you can. And I have in previous years had simpler transfer functions where it ends up being second order. Just set your expectations appropriately. Yeah. Okay. All right. So now we've basically changed the shape to make sure it goes through this point, and now we want to directly place the pole at this location, right? So before, if we go back a few lectures, we calculated a value of k such that the closed loop poles lie exactly on the imaginary axis. to understand stability. And how did we do that? What tools did we use there? Yes, Justin. Exactly. So Justin's saying that for the case of when we're looking at the value of k such the system is just marginally stable to understand what limits k can be before it goes unstable. Now, note this system doesn't go unstable, right? I can crank up the gain to infinity, and the poles never move into the right half plane, right? They actually just, two of them just keep on going farther and farther left half plane before it goes to this asymptote. The other one terminates at the 0. All right, so we don't necessarily have to worry about stability for this problem, but we can use some of the same methods. And so Justin's saying that in the case where we're looking at when it goes unstable, we're drawing vectors to this location to understand the magnitude criteria. And so we're going to do exactly the same thing here as well. Is we're going to say, we know that this is a very geometric interpretation of the root locus plot, where we know from previous lectures that k, or say magnitude of g of s, is equal to 1 over k. All right, so if this is true, that means that this point is on the root locus, right? So this allows us to compute k as the inverse of the magnitude of g of s. And going way back to lecture 2 and homework 1, we know ways in which we can calculate the magnitude of some sort of function of complex numbers by looking at a bunch of vectors going to this point in the complex plane. So we say here is s. S is equal to negative 4 plus 6i. All right, so if I draw a set of vectors running to this point, all right, and I'll just label these in sequence, R1, R2, R3, R4. We can calculate then magnitude g of s. Right? So keep in mind we have to understand what's the innate gain of the system. So the innate gain of the system is actually just 1. Right? So this is now in pole 0 form. Now this wouldn't necessarily be true. You could have plants with some different innate gain, but this one has a 1 out front. Right? So that makes this one a little bit easier. So if I calculate magnitude of g of s, that's going to be equal to the magnitude of these vectors of all the zeros, that was R2, over the magnitude of the product of all the poles, R1, R3, R4. So this is coming from, if we have a transfer function g of s, the way in which we are using this is we're looking at this in terms of pole 0 gain form, which is of this form. So you have a set of zeros, you have a set of poles, right, on and on and on, right, and then the coefficient out front is k hat, right? And if we look at matching this up to our problem statement, or this right here, same thing, set of zeros, set of poles, right, and the gain out front would be 1. Okay, so then looking at R2, so R2, if we look at the real part, is the real part of 2, imaginary part of 6, right? So this is going to be then square root 2 squared plus 6 squared. Sorry, that's not drawn very well. All right, from the plant, I had a pole at the origin, I had a pole at -1. So that corresponds to having real parts. For the pole at the origin, this has a real part our real part of that vector of 4, imaginary part of 6. Pull at -1, I have real part of 3, imaginary part of 6. And then the very last one, I have a pull at 34, right? And it's the difference between 34 and 4 is 30, so that means a real part of 30, imaginary part of 6. So throw this in the calculator, you're going to get then 0.03 or 0.0043, and then if I say that k is the inverse of that, equals 234. Any questions about that last part of the design process here? So just putting this all back together, this means that our controller, k lead of S is equal to 234 S plus 6, S plus 34. Justin. Exactly. So the very first thing you always have to concern yourself with is stability, right? And we saw that the locus plot is always in the left half plane, right? It never goes into the right half plane, so that largely alleviates that fear. We'll talk about margin of stability next week, and so we'll add a little bit more nuance to that statement. But at least if the system behaves perfectly in an ideal manner, right, it'll never go unstable no matter what your gain is, based off the root locus plot. So this is saying, all right, we care about performance too, which is our metrics to the step response. Let's choose closed loop pull locations to make sure we hit that metric. Okay, so I think it's helpful to look at this in software. So I'm going to pull up MATLAB here. All right, so our plant, G2, is equal to a system that has no zeros, right? This is the empty vector here. Then we have a pull at 0, a pull at -1, and no gain to the system. Say what? Does not like the command ZPK. Oh, I'm missing the gain. Thank you. All right, there we go. All right. So then this is our plant. If we want the shortcut to making sure that this is identified as a plant, is you give this as the argument to CISO tool. It'll make this the plant for us. When it pops up in a second. Okay, so it generates the root locus plot, and this is the root locus plot for proportional control, which is, it'll pop back up in a second, which is exactly what we drew. And if we want, we can start to add our design constraints to the system to understand how well it, basically understand the problem a little better. So if I want to add design constraints, trying to remember what they were. So natural frequency of 6. And then overshoot of 20%. Okay. And so here, just to kind of reiterate what we saw when we drew this by hand, we saw that no matter what our gain of our system is, it's never going to go into the desired area, which is the area that's in white. Right? So the area in yellow is the area we do not want the closed loop pulls to be. We see we cannot move it into this location. Also, we can add design constraints on the step response too, if we want to visually see how well we're doing here. So we said we wanted a rise time of 0.3 seconds, and we want an overshoot of 20. All right, and so then we can see that kind of some things that we can see that we can start to meet this rise time constraint if we increase the gain a little bit. All right, so there we're definitely meeting the rise time constraint. Whoops, it's overshooting a little bit. All right, move it back to here. Okay, so here we're meeting the rise time constraint, but the overshoot is nowhere near being satisfied, right? It's way overshooting that response. Okay. All right, so this is where we started in terms of proportional control. We see that this is not going to work. So then we can add controllers, or a compensator to this. And so that is in this block C. So if you ever need to know what the architecture looks like, you just go to Edit Architecture, and it'll show you what all these labels mean if you forget what F, C, G, and H are. But C is the controller in terms of how MATLAB specifies it. And so here it shows that the way I manipulated that currently has a gain of 45. We're going to change that in a second. All right, and then you can right-click on Dynamics, add pole zeros, and you can do a lot of different things, in terms of like adding real poles, real zeros, etc. But the shortcut one is you could actually compose this of individual poles and zeros if you want. The shortcut is say add a lead controller. And it's going to give you default pole and zero locations of a 0 at -1 and a pole at -10, right? Which is not what we designed, that's just the default. So we make this at 0 at -6, pole at -34. And we can start to look at the response. And then the other thing we have to do is you have to look and see how MATLAB is representing this. All right, so I don't know how clear that is in the back. All right, but it's putting the basically, instead of how we wrote it in this form here, where it's a little bit easier to determine what the pole and zero are. And so we have the coefficient that is not equal to 1 is on the s to the 0 term, not the s to the 1 term, right? And MATLAB does exactly the opposite, so we have to convert between the two. And so we have to divide the top by 6, the bottom by 34 to give us. This is equivalent to 41, approximately s over 6, plus 1 over s over 34, plus 1. All right, so to use MATLAB tools, you have to use it the way they want to see it. Okay, so our actual gain we're going to enter in here is 41. Okay, so we can see a few things here. We'll talk about the step response and why that's just a little bit off in a second. Let's talk about the locus first. All right, so this is essentially what we drew. Let's see, how do I get this? The location here should be almost exactly at. Now we did some rounding, like 41 is not the exact number, but this location here should be almost exactly on -4, -6. So it may be really tough to see. People in the front may be able to see this, but at the very bottom right, if I hold my pointer on this point, it'll show you where that current location is. And it says -3.97 minus 5.9i, or 98i. So very close, because 41 was not an exact number. It was just approximate. All right, so we essentially placed it exactly where we want the pole, close of pole to be. We see that the other close of pole is pretty far in the left half plane. Now to note, we do have a 0, and this 0, because it's an open loop 0, because it's in the controller, is going to be a closed loop 0 as well. And we know that zeros in the left half plane are going to increase the overshoot a little bit. All right. So it's not acting perfectly like a second order underdamped system. It has extra dynamics. So this closed loop pole probably insignificant because it's so far away, but the 0 that remains is affecting the dynamic sum. So if we look at our step response, we see that we meet the rise time just fine. We're a little bit high on the overshoot. Okay. So So this, I would say, gives you something that's very, very close. We are much better than we were with this design methodology. Gives you something very, very close. If you ever want to exactly get this, you have to do a little bit of manipulation to get this to work. So the manipulations that I did for this exact problem is, let's see what I do. I move the 0 to the right a little bit. Move the pole a little bit farther to the left, and the gain got jumped up to 54. Thank you, that's very high. Okay, and so then looking at this step response again, we see something now that's satisfying all those, right? So it got us very, very close. We had to manipulate these a little bit. That's why the software tools can be very helpful. So in terms of like getting something where you say, all right, I don't know what to do, getting this confined to some answer that's going to be close, this is a good way to do it. So analogously to a lot of the tools you may be learning in mechanics and materials, you use all simplified expressions of what a construct looks like, and then if you're at an engineering company that has a lot of resources, you put it in finite element tools to really understand truly what the stress values are. Same thing as this. The calculations will get you very close, so you have an idea of how to window onto that design, and then software tools can help you the rest of the way to make sure it satisfies those constraints. Okay. Is there anything else I want to say on this? Okay. Any questions on what we did here? Okay. Yes?
Would ever be exact, like doing this, whatever, like, be right, or is it always just going to go slow?
If leak control, no, it's never going to be exact. Because with leak control, you're always adding, so all these metrics in terms of windowing out the complex plane and saying, all right, this pole location will give you this step response, that's for a second order under-damped system. And so even if we had, say, for instance, we had a system with just a single pole, the lead's going to add an extra pole, so we have the potential to be second order under-damped because it has 2 poles. But we've also added a 0, right? So it's always going to have extra 0. And so it's going to be slightly off that. Yes, Karsten.
The MATLAB default pole and 0 locations also distorted such that the asymptote was in the acceptable region. So would that be preferable so we don't have such a large gain value?
So I don't know what it looked like. I wasn't looking at where it was when that was in that configuration, so I'm not sure. But the default is just at -1 and 10. It's very arbitrary. Sort of in terms of one being 10 times the other one. I would suggest that you probably have to do more than just use the default. Yeah. Okay, any other questions on this before we move? We'll get just like an introduction to lag control, that's it. More of that. Yes?
Wouldn't change the MATLAB again for it to work, because initially you just put like -6, -6.
Yeah, so just slightly moving the zeros and poles around. So this is -4.2, -36.5. So
When you first added in,
sorry?
when you first added in the lead controller, you said MATLAB didn't like that format for it, so you had to change it.
Oh, when I typed it in the command window. Oh, I forgot the gain. So if you look at, here's my first time I typed it in, I didn't have 1, and this time it did.
I meant like the K-lead instead of the lead. Sorry.
Lead control instead of controller, you had to reconfigure the way it was formatted.
Oh, I see what you're saying. Okay. Yeah. Okay, so this is how we wrote it, right? This is our work. And so MATLAB wants it in this form where the 0 and the pole are represented as the coefficient on S, not S to the 0 term. So we just had to rewrite. These are exactly equivalent, right? So I just had to rewrite it. So divide the numerator by 6, or pull out a 6 out of the numerator, pull out a 34 out of the denominator.
So did you just type in -6,
Yeah, and I forget if, I don't actually remember if, I'll have to remind myself if I can do math, if you can do math in there. So I don't know if this would work if I do, whatever it was. 234 times 6 divided by 34. Yeah, okay. You can just do the math right in there if you want. All right. The other thing, sorry, thanks for the pause too. I forgot I was going to show you this. So this tool is nice because I can just, if I want to look at different gains, I can just kind of move around these pink dots, right? And it changes the pole location. So I can just kind of drag them along the root locus. The other thing too is that you can change your design. Like the plan is fixed, right? So it's coming from the idea that that's usually hardware, that doesn't move very easily. But I can move this 0 around as well. And so that's going to actively distort the root locus for you. So you can see how as you move a term around, how the root locus changes in real time. Which I think is good pedagogically too for teaching, trying to understand like how pole and 0 locations affect this, right? So it shows you how this is distorting in real time. Yes?
So for a lead controller, is that design change pretty much strictly virtual, like changing code?
Yeah, we'll be changing code. Yeah. I think that's a good question. I've had previous years I've had students ask, okay, you keep on saying you're just changing code. What do you mean by that? All right, that's kind of arbitrary, right? So if we look at, this is well outside the scope of this class. This is getting into, if you really want to learn this really well, you would take digital control, which is a 7,000 level graduate class. All right, so it's really getting up there. So that'd be probably only if you go to graduate school at Ohio State, you could get into that sequence. It'll take you a few classes to get. But the shortcut to this is MATLAB has some built-in tools to get you, without really knowing what it's doing, it'll get you an answer that you can actually directly code in. So our design for our G1, we said, was equal to ZPK. Let's start with the very first one, just as a starting point. And this is then 234, I believe. Yeah. All right, so this is what we designed for our controller, G1, right? So basically gain, pole, and 0. And then if you want to ever get this into digital form, you would do then, so G1D, we'll call it the digital one. This is equal to C to D, which means, C to D means continuous to discrete. So it's going to change it from continuous time formulation, which is what we work in this class, to now something you can actually directly integrate into a computer. And then we say the argument's going to be G1, and then we have to say the sampling rate. So a very common sampling rate for robotic systems is 1 kilohertz. This is updating 1,000 times per second. And so you type this in, and it's going to kick out an equation for you, and you see that what was in a variable of S is now in a variable of Z. And so Z, when we work in discrete time, is how a computer works. That's just the frequency variable when you work in discrete time. There's a lot more to that. I'm glossing over that very, very quickly. But that is what the form would look like. And then what this, how this can be literally interpreted. So this, doing inverse Laplace transforms, I would say, is fairly difficult. Doing inverse Laplace, it's not really Laplace transforms, but doing the inverse transform in discrete time is actually really simple. So we said that G1 D, in digital time, this is a function of Z. So more 6 is equal to this, right? So I'm just copying down what's in MATLAB so we can show the correspondence between them. All right, so this is just the form. This is just transferring this into discrete time. And so this just like in continuous time, this is output, which is the input to the plant, over input, which is the air signal, right? And so now if we multiply these out, just make this clear, this is a minus sign. Oops, made a mistake. This is U, and then this is 234 Z minus 0.9941 E. All right, and so this actually literally means time shifts. So if you do a Z to the first power, that's a time shift of 1. Z to the second power, a time shift of 2, and on and on and up. So this means that if we have some sort of signal U of K, right, that is my discrete time signal. That's going to be the intimate to my plant. And I also have a signal E of K, right? So this is stepping in time. So time step 1, time step 2, time step 3. That's how a computer works, right? In terms of going in time steps. This would then be U of K plus 1 minus 0.9666 U of K is equal to 234 E of K plus 1 minus whatever 9941 is, 0.9941 is times 234 E of K. Right. So you would have somewhere in your computer that the next time step that you're going to send out of your data acquisition system, if I rewrite this, this is the next time step I set out, is going to be equal to what my previous time step was, if I move this over to the right-hand side. Plus my previous error signal, or sorry, my current error signal minus my previous error signal times some sort of gain. So it creates this recursion, right? So the next output of my DAC is equal to the previous one plus some sort of multiplication of previous error signals. So this is how you would actually ever integrate this into a microcontroller. But as well outside the scope of this class, it's just kind of just a practical aspect of this. And so you may also look and say, okay, the poles of this transfer function are in the right half plane, right? And so you say, how can that be? We said that this controller is stable because all the poles were in the left half plane. Now they've moved in the right half plane. So that's a completely different story. But basically, in continuous time, we say that this is the stable space in the complex plane, right? Left half plane. And in discrete time, it's actually the unit disk. So if your poles are inside here, it's stable. And if it's outside the unit disk, then they're unstable. So completely different analysis method. Again, well beyond this class. So.
That way everything's under one.
Yeah. Yeah. Exactly. Okay, that was a fun little side. We have 5 minutes left. Okay, so lag controller design. So we talked about lead controller. We gave one example. You're going to have examples in your homework. You're going to have examples on your project. You'll see plenty of examples of this. As you can imagine, some of this requires calculations, right? Some of them, the calculations are difficult. This will be clearly defined in a test in terms of how to handle that. Say, oftentimes leaving like gains in the form of radicals, or leaving things in terms of inverse tangents, right? So we're looking more at the method on a test, not necessarily what your actual answer is. So that will be clearly noted. We'll give you examples that kind of show how that would be expected to be represented on test. All right, so lag control design. So a lag controller is an approximate form of a PI controller. So what's the purpose? Reminder, what's the purpose of a PI controller? What's the integral term do? Yeah, so at steady state, make sure that the air goes to 0, right? That's the whole idea, right? And so it has, we talked about some of the issues with it in terms of making systems potentially go unstable, but it doesn't always, you can definitely design PI controllers that are not unstable, but you have to worry about that. So same idea here. So this is an approximate form of a PI controller, also called lag compensation, just like lead controller, you can also call lead compensation. And the purpose is to remove or lessen steady state error. Okay, so a lag controller would not completely eliminate steady state error for you, it would just lessen it, but it's still very beneficial. So just as a reminder, making a comparison to something we've learned already before, if we said we had a lag controller, it was in the form of G1 of S. Sorry, if we had a proportional integral controller, we had the form of G1 of S is equal to Kp plus Ki 1 over S. All right. If I want to write this under a single denominator, I can write this in terms of, in a single gain, I can write this as some sort of gain out front over S, 1 plus Ts. And so we'll get into what T is and how that's important in a little bit, but we can then write that K would then be equal to Ki, making these equalities true. So that's sloppy. And then T is equal to Kp over Ki. Okay, so lag controllers have a fairly similar form. It's going to be slightly different. But we have G1 lag of S. And you're going to say, I'm going to write this, and you're going to say, why is this any different than the lead controller? It looks exactly the same. All right, this is the exact same form of our lead controller. The difference here is where our 0 and pole are. So in the case of a lead controller, we had a 0 being less than the pole, and this is going to be the opposite. That the 0 is going to be farther away from the origin than the pole is. So we just flip the order of them. So lead controller, lag controller, same thing, just flip the order. That's it. But it's going to have, by flipping the order, it changes the action of it considerably. All right, so the pole, just for your notes, is at negative PC, 0, negative ZC, so that has this shape in the complex plane. Okay. Karsten.
So, in the previous one, we defined K to just be Kp. Why do we define it instead of Kd? Why do we define it K as Ki in this case instead of Kp?
So what we're doing here, I think I get your question. So what we're doing here is we're trying to find an equivalent way to write this, such that we have a gain out front, and then it has pole zero form. We have just polynomial in the numerator, polynomial in the denominator here. So just writing in this form, and it just so happens that by writing this, K is equal to Ki. If you go back to the other example, if we write it in a similar form, that was the term that was the gain out front. So just looking at equivalent forms, nothing more than that. All right, we're out of time. Good luck in your measurements test. See you on Monday.